My name is Alexandre Meurice. I'm a space resources scientist at the European Space Agency, and I will be co-chairing this session with Jennifer Heldmann, who is also our first speaker. And she will speak about science exploration and public engagement from the NASA SSERVI resource project. Jennifer, I think you can get started with this 8 minutes plus 2 minutes question.
Great, thank you very much. Got my timer going, so I'll try and stay on time. So many thanks to you all for joining the session about ISRU. I'm going to take the next few minutes to tell you about some of the work that's going on under the resource project, which is a SSERVI team. So many thanks to SSERVI for funding and supporting this work. So the entire premise and sort of setting the stage for this session is that ISRU, near the sites where we have robotic and/or human missions, can enable sustained and affordable exploration of the moon, Mars, asteroids, and beyond. So in order to use the space resources, we need to know their location, their quantity, their distribution, and extractability. So some of the work that I'll tell you about that's going on under the resource project is looking at the operations and hardware associated with the different ISRU steps, including prospecting, excavation, transportation, processing, that all have to be examined, tested, and integrated in order to enable effective ISRU. So I won't read all these words, but it's here for posterity. These are some of the key tasks that we're doing under the project itself. On the right-hand side, you can see some of the high-level topics as outlined in the SSERVI parlance. So some of the things we're doing, assessing and characterizing resource inventories on SSERVI target bodies, and working to develop a semi-quantitative mineral potential model to assess the resources, focusing on water ice on the moon, and trying to integrate the different data sets that we have to identify the form, the character, and the distribution of the resources. We're also doing some hardware development, ISRU technology development and testing. So I'll tell you a little bit about a prospecting payload to develop borehole instruments integrated with drill systems, and also some really exciting hardware development happening at NASA Johnson to look at the entire ISRU water processing system. We're also doing a lot of work to understand how we would conduct these robotic and human missions, looking at concepts of operations, capabilities, and the human-robotic interactions. So we're looking at things like augmented and virtual reality, human-machine collaborations, human factors and engineering functional task allocations to try and optimize how we execute these missions. And then doing work on the future robotic mission support activities, specifically what you need in your ground data systems to make these missions happen. So just to highlight a few of these different areas, one is the application of geostatistical methods. So this is to build up predictive capabilities so that we can understand where these resources may be and if they're viable to use for ISRU. To do this, we partnered with the USGS, who has been prospecting for minerals on Earth for over a century. So what we're doing with USGS, you take the different data sets that we have in the lunar case, for example, lay these all on top of each other and combine them to identify different areas of different resource potential, prospective, favorable, permissive, non-permissive, and trying to understand the certainty that you have with that and also the level of resource potential. And we're doing this, that's called mineral prospectivity mapping, MPM methodology. Use these data sets and weight them appropriately to determine how well or poorly you can predict where these deposits will be, right? We don't have ground truth everywhere that we might want, so we need to build up the predictive capabilities. And so we're really building on the terrestrial examples for how this is done in the mineral world and applying this to the moon, Mars, asteroids, and beyond. Another activity is looking at next generation drill development, for example. So we're looking at ground truthing and changing the paradigm for how we do this. We're bringing the instrument to the sample in this case, instead of drilling down and bringing the sample up to an instrument. So working with Honeybee Robotics is doing the heavy lifting on this part of the project, leveraging flight drills, the Viper drill, and instrumentation that's flying on multiple CLIPS missions and Viper. And so integrating a near-infrared spectrometer, a neutron spectrometer, temperature sensors, and a DSP probe and cameras into the drill itself. So as you drill down, you're collecting that data in situ and getting higher fidelity information and less sample handling and processing. Also, a really exciting project is using the PVEX drill, also through Honeybee. And so this is a coring auger that has heaters internal to the drill. And so essentially, as you drill down, you evolve these gases, and these gases then go back up to the surface, and then you can send them anywhere you want. Send them into your mass spectrometer for analysis. Send them to a cold trap for looking at production for ISRU processes. So there's an example down here where at Honeybee, they basically caught these volatiles in a balloon to show that you can go down, you can heat these volatiles, evolve them, release them, and then capture them after the fact. Here's some more hardware development that's happening at NASA JSC. Aaron Paz is the lead for this. And so essentially we're looking at using hardware for the entire end-to-end demonstration of what you would need to do for ISRU. So starting with the extraction process, capturing the water cleanup, the electrolysis, send through the oxygen dryer, and then liquefaction. So doing kind of the soup to nuts of what you would need to do, and using existing hardware where possible, and then development of new hardware as needed. There's some other work also looking at advanced capabilities. I'll just give you one example here, looking at virtual reality. So right now, this is work being led at MIT under David Newman and her group, focusing on depth data and imagery acquisition to render lunar landing sites in VR. So what we'd like to do is to have high fidelity data and information so that we can see these sites and do science analysis, right? So you can do measurements after the fact, and also use this data for tactical decision making and traverse planning and making decisions during missions, for example, robotic rover missions. So just as a rendering of how this would play out, here's a video if it will play. There we go. So this is the concept where you have your rover on the surface of the moon, right? You've collected this data, and we're doing the trades right now to look at the optimal camera systems for collecting the data, you know, considering bandwidth constraints and comm, et cetera, et cetera. And then you can render your site in VR to do the science and to do the mission operations. And of course, if you've got this digital environment, you can overlay different layers and different types of data. So here we'll just put an elevation map on, for example. And then it can move around in here, and you can imagine that you're putting on multiple different types of data layers as well, including data that's collected from the rover. So we've been doing that as well, particularly with the near infrared and neutron spectrometers to start overlaying the data on the field site, and doing that in terrestrial settings at some of our terrestrial field sites, and then looking at the lunar application case as well. Trying to advance out of the movie. Nope, don't play it again. Okay. And I also, just in the last minute or so, wanted to touch on some of the outreach that we're doing. And this is some of the educator engagement and increasing representation within STEM, within planetary science, and within the ISRU community. So we have co-Is, Dr. Alexandra Maziela-Novak at Johns Hopkins and Dr. Dina Khalil at Howard University are really leading this work for us. Alexandra will be giving a talk tomorrow about this, so she will talk about this in much more detail. But developing virtual communities of practice and trying to bring in underrepresented groups and students, and focusing on the teachers who then bring that into the classroom. And we're trying to interface with different groups in this way. And one of the really interesting activities to broaden the participation and bring in minoritized groups is to do culturally relevant engineering design challenges. So we have been doing this under the leadership of our outreach leads. And we're trying to have these students access the material in meaningful ways for them. So looking at it in a lens, for example, of social justice. We're looking at, you know, water resources, and that's an issue on Earth as well. How do you have clean water for other people? How do we get that on the moon? How do we actually clean the water? How do we identify the water, et cetera? So there have been different design challenges that have been developed. And if you go to Alexandra's talk, she will certainly talk about that more. And also increasing field accessibility. So this is one of the things we've seen in the pandemic. We haven't been able to get out into the field. And so we've been looking at technologies and developing field courses that can be done remotely. So there's some examples down below, and we've teamed with the University of Idaho doing some of this. and opening up the field of geology to people who may not be able to go out into the field even under regular circumstances. And then bringing that data in and enabling more science to be done. And then just real quick, commercial partners, I'm really pleased to be working with these groups, with Honeybee Robotics, looking at planetary drilling and the next generation of instrumentation. Astrobotic, because we need to understand and think about how we take these hardware development pieces and these new technologies and integrate them and fly them. And that goes for iSpace as well, which is really predicated in using ISRU for the moon. So with that, I think I can end and hopefully not be too over time.